Very good morning to all of you. It's wonderful to be here today, and this is incidentally my first visit to IISER Berhampur. Thank you very much for inviting me. It's a great pleasure to meet all of you young faces and to talk about something which many of you may not be interested at all. So this is a challenge that I take up to make you a bit interested in earth sciences, one aspect of earth sciences. And so let me give you a little bit of background of myself here with respect to IISER. You know that the IISER movement started way back in 2003-04 when the government of India decided to have new institutes which are blends of academic and research. And then IISER Kolkata was the first one, along with IISER Pune, to be established in 2006. And the Earth Science Department started in 2009 in IISER Kolkata. That was the first one. And I was fortunate to be Associate Institute and the department, so I know in general about IISER. And so, thank you once again. And what I am going to talk about, what I understand some of you are earth science students, but not certainly all. So I have made the topic and the discussion in rather simple scientific way so that anybody should be able to understand, because I have used minimum amount of technical earth science terms in the talk. So the topic that I am going to talk on is chemical equilibrium and disequilibrium to monitor mountain building processes. Okay, so the first two things, chemical equilibrium and disequilibrium, you know better than me actually, because I am not a chemist or a physicist, so I had to learn all those things. So you know better than me. And regarding the mountain building, all of us know about mountains. All of us must have inquired in our mind that how the mountains are built. So about that I am going to talk a little bit, and the first few slides are very general slides about earth science as well as about the chemical equilibrium and disequilibrium. I am not here to teach you chemical equilibrium or disequilibrium, but I will tell you that these simple chemical principles, how far I can extend it to the application of some very exciting problems. So that's the purpose. It's not the purpose to teach you chemistry at all. And perhaps I'm not qualified at all. So I've taken 4 minutes for this starting. So you, in general, in your very first class of earth science in general, you are taught about what is earth science. And I have highlighted two words in red, and I am concerned in this talk about these two, that how the earth evolved and how it works. A part of that. I am not touching about the origin of the earth or the sustainability issues here in this talk. So we will consider that how mountains are formed. Mountains are part of the earth, so how they are formed and how they work, how they look like, what they look like now. And if you cut a section through the earth like an apple, then of course you see these things, that the earth is compositionally and physically zoned, in the sense that there are different layers within the earth. You know that we call crust, mantle and core. And How do we get this? Largely from geophysical measurements or the propagation of earthquake or seismic waves. That's how we have determined those depths and the compositions as well. And we will be talking about the Earth's crust. Earth's crust is about, on an average, 40 kilometers thick. The upper part, the word crust means the upper part, like the crust of a bread. So that's the 40 kilometers, but the maximum is 90 kilometers beneath the Himalayas. That's the maximum depth of the thickness of the crust. The crust is followed by the mantle below and followed by the core. Now, the part of the crust and the part of the upper mantle is constituted of what we call lithosphere, and below that comes asthenosphere. That's what you can see here, that you
point won't work on that. Screen it won't work.
Okay, so the upper part of the Earth's crust, the crust and the upper part of the mantle constitute what is called lithosphere, and this is the thickness of the tectonic plates. All of you know the plate tectonics and other things, and that is the thin plates of the part of the crust, Earth, which moves with respect to each other. That is the plate tectonics, and below that is the asthenosphere. Now the difference also lies in how the Earth loses its heat. The upper part of the Earth's crust, that's the lithosphere, loses the heat by means of conduction. It's a thermal conduction. It is losing the heat to the atmosphere. And below that, when you look at the asthenosphere or the lower mantle, then the Earth is losing heat by convection. And so the mantle is something very interesting. It convects. It convects means it is not rigid solid. So it is a very high density fluid actually. That's the beauty of the Earth's mantle, because it can convect. And the boundary between the lithosphere and the asthenosphere is also the boundary between the two modes of heat transmission, from convection at the depth to conduction. Now we have the plate tectonics in 1970s, and I grew up because I started studying my undergraduate course in 1968, which is almost the time of the plate tectonics coming into. So I grew up with plate tectonics, and I was obviously very thrilled with what was happening around me at that time. And so what is plate tectonics? That is connected with the rigid upper part. Why rigid? Because the heat is transferred by conduction, so it is rigid. It is not convective mantle, which is not that rigid. And then the plate tectonics provides us a very unified vision of how Earth's oceans formed, how Earth's mountains formed, among many other things. It gives you almost answers to almost everything, that where life formed, how it formed, how mountains formed, how oceans formed, everything, how mountain evolved. So the plate tectonics is the unified theory in earth sciences that we use to interpret every feature on the earth. And these are the plate boundaries that we have on the earth. So you know all that, so I skip this and move on to the types of plate boundaries that we have. The different plates must have boundaries. So we have plate boundaries where the two plates come towards each other, we call convergent plate boundaries. Where two plates move away from each other, we call divergent plate boundaries. And where the plates just slide past each other, we call transform plate boundaries. So we have three different kinds of plate boundaries, and these are really shown on the Earth, the map of the Earth, the different kinds of plate boundaries. You can see that the convergent plate boundaries were located between the two continents, and the divergent plate boundaries are located mostly in the mid-oceanic reaches. You can see the mid-oceanic reaches like this. These are the divergent plate boundaries. Now, in this work, today we will be mostly concentrating on convergent plate boundaries. And coming to the topic now at last that we are going to talk is that about the Himalayas. Now, we all know that the Himalayas formed due to the collision of the Asian plate with the Indian plate. So this is depicted in a very simple diagram like this. Now, so this is how things happened. Now, I am sorry to here introduce a few small terms. For example, when two plates converge means they collide, and when they collide we call a mountain is formed in between. Like when India and Asia collided, Himalaya came in between. So what happens during this collision? This collision, there is a very large scale deformation. You can understand two huge things colliding. So how much energy will be released? We are very glad that we are not there at that time, definitely. Now, even a slight movement causes so much of devastating earthquakes in the Himalayas. A slight movement is not a collision. So we shudder to think that what happened during the collision. Fortunately, we are not there. Then there will be a lot of magmatism, that is formation of volcanic rocks, volcanoes, and the formation of igneous rocks at depth. So that's why I generally call it magmatism. And thirdly, what will happen, since one plate goes down below the other plate, the rocks get buried, and they change in pressure and temperature. So they are, so to say, metamorphosed. So we have metamorphic rocks. And the path of the metamorphism will be something like, you can see what we call clockwise. You can see from left to right it is moving. First the pressure increases, and then the temperature increases, and then it comes up. That is obviously it comes up. Obviously, because the mountains are sitting right on the Earth's surface. So they have come up, no doubt about it. So these are the three things that happen during collision. And the collision takes us, one of the examples, to the Himalayas. This is where we went in North Sikkim, one of the places that we went. And I'm happy because I studied mountain building, because I was fortunate to go to this place, which is almost a paradise on earth, I say. And this particular place is in North Sikkim. Those of you who might have traveled to North Sikkim, this is Gurdongma Lake near the Chinese border, 6 kilometers from China. And then while we were picking up rocks and studying, we found that this rock sitting at the top of that mountain has minerals which indicate that the rock was metamorphosed or formed at a temperature of more than 800 degrees Celsius and at a depth of nearly 33 kilometers, equivalent to 10 kilobar pressure. So these are the numbers, temperature and pressure. That was the conclusion of the work. Now I am going in a reverse direction today to tell you how we calculated the pressure and temperature. So I first give you the number and then I tell you that how these are calculated. So the point here is that how do we get these numbers? Why 800, why not 600, why not 200? So first question we are asking today, and to answer that question we invoke equilibrium thermodynamics. So here comes the application of chemistry or the chemical principles to Earth system science. So that's why we call it an Earth system science. It is an interaction of different components of the Earth using the fundamental principles of physics, chemistry, biology. So the principles we are using are physics, chemistry and biology in different fields, and we are doing some bit of mathematics as well and statistics as well. So earth science is, so to say, a hodgepodge. But it is answering so important questions because all of us have seen the mountains. We must know that how that rock which is sitting at the top of the mountain came at the top of the Earth's surface. If it has formed at 33 kilometers, how could it come up there? How fast did it come up? All these questions crowd my mind. And for that, we will use a second principle, which is disequilibrium. I am coming to that later. And so the first thing is that I wrote certain numbers, and you have every right to ask me, how do you get those numbers? So that's why we are indebted to this gentleman, J. Willard Gibbs, who in 1839 onwards actually provided the first very solid application of equilibrium thermodynamics to natural problems. So it was not a problem in the lab. He took it to solve many real life problems. One of these was the mountain, this pressure temperature calculations, which were actually formulated by the names which are given later in red. They are the pioneers, and there are other pioneers. I just wrote 4 names. There are other pioneers as well. So what they were using, and Gibbs was of course a chemist. He's not an earth scientist. He was a chemist. And he could visualize that this chemical principle has got applications to solve natural science problems. It's not only chemistry. So that is the greatness of a person that we talk about, when one can think beyond his or her time and see the future. He saw the future, and then the simple principles of your equilibrium, we all know the definition of equilibrium, so I am not going to teach you, but you know the basic concept is that delta G, the Gibbs free energy of a reaction, must be 0 at equilibrium. So the reaction, both the reactants and products, they don't change composition, so it is fixed. And that translates into the second equation, d mu I is equal to 0. There is no change in chemical potential. Because if there is a change in chemical potential, there is a flow of mass from one side to other, then there is no equilibrium. That's the simple thing. And that gives us to a very important relation which all of you know is the Gibbs-Duhem relation. And this we will use actually. We are using it. This is the chemists they gave us. And now we are using it for earth science problems. Like from the Gibbs-Duhem relation, I derived the Clapeyron equation or the Clausius-Clapeyron equation. The pressure temperature slope is given by del S by del V. You know that. Now what is very important? Del S by del V, if I know the change in entropy or change in molar volume of any reaction, then I can calculate the slope of that reaction in pressure temperature space. So I can do that. That's a revelation. And so if I have two reactions on the left side, so please look at the left side diagram. If you have two reactions which are plotted in pressure temperature space, one has got shallow slope, another steep slope. So the change is in dP dt is change in del S by del V. So the reaction which is vertical must have change in del S more than del V, and the reaction which is subhorizontal must have change in more in del V than del S. And we know entropy is related to temperature and volume is related to pressure. This we know. If I increase pressure, volume decreases. If I increase temperature, entropy increases. We know. So actually by looking at entropy and molar volume, we are trying to look at the effects or the controlling parameters. And the controlling parameters are pressure and temperature. Because remember, the question that I asked is how do I get those pressure and temperature values? Now these del S, del V or entropy, molar volume, enthalpy of all natural minerals are now experimentally constrained. We have tables of all now experimentally constrained. So we have the data. Now we have to do some calculations to solve our problems. So unfortunately, not all the minerals that we study, they are pure end members because we are not producing them in the lab. So what happens is that they are already produced in nature, so their compositions vary. And naturally, we have to look at the chemical potential variation. And in equilibrium, there is no change in chemical potential. Of course, reactions cannot move from this side to that side. And we use that to derive a major reaction called Van 't Hoff isotherm that you know is the relationship between energetics and composition. Delta G is the energetic change and K is the equilibrium constant, so it is the composition. So see how we are zeroing down to natural rocks and minerals or the natural material. We have now come from energy to composition. Composition is something I can measure. Down below there is an electron probe microanalyzer with which you can easily analyze compositions. So now you have two terms, one side is energy, other side is composition. I determine composition, I calculate K, and I have experimental data on delta G or HSV. So now I combine them to solve for P and T. That's what I am doing simply. And then I get this general equation like this. From the Van 't Hoff isotherm, you introducing the effect of pressure on volume, I have this reaction ln K function of pressure and temperature. You know equilibrium constant is only a function of pressure and temperature is this, and then just switching off terms I get T is equal to this and P is equal to that. So see, right hand side you have two things. One is energy terms H, S, V, etc. This you can get from the tabular form of the minerals by given from experimental data. We have big tables, we have those. And the other side is K. The K is determined from composition. So I have to go down 2 floors below and analyze with your electron probe to get K. So I have K, I get this. So I can solve theoretically for P and T. So this is what we do now. We call it mineralogical thermometry because we are using minerals. As simple as that. So these are the hypothetical reactions we write of 2 minerals and member reactions, and then these are of course natural minerals, and then we use this temperature equation of the previous one, and then we have this formulation. So you have to get the chemical composition, calculate the distribution, equilibrium distribution coefficient Kd or K, so to say, and then you calculate the T. So this is one type of equation. Another type of equation we can use to calculate P. You remember that we need 2 reactions. One is steep, which is very sensitive to T, and one shallow, which is very sensitive to P. So this one is very steeply sloping, so this is sensitive to P, and we have this kind of reactions, we call them net transfer reaction. Doesn't matter, don't bother yourself. Don't bother yourself with the names given. Consider it A, B, C, doesn't matter here. But the question is, this is the principle with which we calculate the pressure and temperature. And when we were a student, we were using calculators. Now, of course, there are huge computer programs. So life has become easier. But there is a problem. Because it has become easier, many students, they use it as a black box. And they don't look at the intermediate steps, which we used to do when we were doing by hand. So at every page we could calculate and see that what were the changes. Now, of course, this is the world of data sciences, so the number of data is much more, so you have to analyze a lot of data, so you need computer programs, no doubt. But the question is, you also have to understand the principle, and you have to understand that how this works, not like use it as a black box. You input something, you get an output, and you just produce a paper. It's not that easy. So that particular thing is a problem. So what we did is that we uploaded these Excel sheets in this particular teaching petrology in 21st century. It's a worldwide thing. So myself and my friend Shumit Chakraborty from Bochum, we actually uploaded several Excel files. The advantage of Excel is that you can watch every step. As you change one value, you can see the output, that how much that value change affects your result. So it is not for research, it's for teaching, in the sense that I used to teach it in the classes, because the advantage is you can see that. While producing papers, you may use the computer programs to get faster results. But you also, as a student, you need to know that how those equations are derived and what are the main controlling parameters. So we use this, and a lot of people in the world has used these things, as I can see from the user list and other things, that many departments use this as a teaching tool. It's not a research tool. And I'm showing it here. You can see the link. So if you are interested, the talk is here, so you can easily do that. And now I go to the second part of the talk, that's the disequilibrium. So disequilibrium means what? The composition changes. And the change in composition must be recorded by the natural material so that I can analyze that change and then only I can apply that change to certain mathematical equations. So I need a change in composition. And the questions we are trying to answer here are regarding the mountains, that how fast that rock, which was metamorphosed at 800 degrees centigrade, cooled, and how fast the Himalayas came up onto the surface. It's a big thing coming from the small mineral analysis done by that your EPMA, which is sitting down below. So you analyze some points and you arrive at such huge conclusions that is related to the entire global scale. So one such mineral we focus is called garnet, which is also a gem mineral, so some of you might be knowing it. In Bengali we call it gomed. I don't know what is the other names and all that, but this is a gem quality mineral, which is a solid solution of iron, magnesium, manganese, calcium, among other things. And this is the composition. Forget it. I am not asking you to remember the compositions, but this garnet is a mineral which shows variations in compositions. And why these variations are caused? Because of change in pressure and temperature. And now they are also recorded in garnet. So I can analyze those compositional changes from garnet. That's the beauty of it. If the mineral is very fast diffusing, then it will homogenize everything. So I will not be able to analyze. And if I don't get a compositional gradient, how do I calculate disequilibrium? I need a gradient, compositional variation. So for that, I need variation in compositions. Now garnet shows two different kinds of variations. One is called growth zoning, which is formed during increasing temperature, and a type of zoning which we called decreasing temperature. This is the zoning of increasing temperature. The four figures are of the same grain, but we are analyzing different elements in each photograph. For example, this one, the top one is, it's given up that I cannot read. It's manganese. I think it is manganese at the top. And this color coding is a function of the abundance. You can see the scale on the right side on each photo. So manganese is very high in the center of the garnet, and it is decreasing away. So this is kind of, we call growth zoning. And there's another kind of zoning which we called down temperature zoning, or cooling zoning developed during cooling. That's called diffusion zoning, and that is, you can see the difference now here. I have taken two different garnets, and in the right side you have a growth zoning. You see the magnesium is low in the center, increasing at the boundary. And the second one is a diffusion zoning, where the magnesium is high in the center and decreases at the boundary. So you can see the two different, so I put those two figures together just to say that there are two different kinds of zoning. You can see that. But these are two different garnet crystals, not that one garnet crystal will not show both. Two different garnet crystals. And theoretically, this is a function of the progress of the reaction, or kinetics, so to simply say. And the progress of the reaction is very low, then 0%, no change in composition, so I cannot measure anything. It's an equilibrium composition. And if it is changed to 100% or near 100%, then also I don't get any path, I get a final composition. So I get a starting composition, I get a final composition. No use. For us to do kinetic calculations, we need the intermediate part, which is shaded here. Here the composition is changing as the reaction progresses, and I'm measuring that progress through compositional changes because I can measure compositions using that instrument. So that's what I am doing now. So I am measuring the compositions in small spaced 1 micron spacings all through. These are the red lines. I analyze 100, 200 points, so I can see the variation, and you can see from the right side that how the compositions vary. So I was presenting this talk in front of chemists in electron microscope, EMSI, electron microscope conference, and they said that it's not possible. I said that yes, it's not possible in the lab, because it's not that fast that the component can reduce because it's in the lab. But here in minerals, in earth sciences, we are thinking in terms of millions of years, not years. So this diagram you can never get in chemistry, not possible. Because in the lab you cannot produce that much of diffusion. It's tremendously slow. But in nature, it's possible. That's why I get this. And then I do a little bit of manipulation. I do not change the composition of both. So what happens that I change the composition of one, the GRT written, and the other one I try to keep it fixed. How can I do that? I can do that if I have a situation where the Bt mineral is much more than the GRT mineral. So then the change in composition of in the Bt mineral is absorbed by the volume of that mineral, so you don't measure a lot of changes. So that's the advantage. So what I'm doing is I'm simplifying a bit the calculation part. I can do both actually, but this is a simplification that I'm doing. And this is the theory of, you know that the diffusion, volume diffusion happens due to how it occurs, and diffusion can occur in the grain boundaries or the boundaries of the crystals through mostly assisted by fluid and other things. So I'm not talking about that fluid assisted diffusion here, I'm talking about volume diffusion, which happens in the solid medium. And then we just solved the two laws of diffusion, Fick's first law and Fick's second law. And please look at the right hand side of the second equation. We have what? Concentration versus x. X is distance. So that's what we were measuring, isn't it, along that line? So x is a distance, c is concentration. On the left side, what you have is c versus small t, that's time. So the two sides are connecting cooling time with respect to compositional variations. The right side I can measure, the left side I calculate. My idea is to measure the cooling time. Why? Because my question was how fast the crust cools from that 800 degrees Celsius. So that we try to analyze from here. So this is a paper we wrote, one of my students' PhD thesis in 2014, and the computer program is given here in this paper. So we solved the Fick's second law of diffusion numerically, and now the advantage of this method was that the input parameters were given by hand, so through iteration. So the advantage was that I was knowing how much I am putting in and what result I am getting. So it was done by hundreds of iterations, but once you do it, then you understand that how much you need to put. So it's not a very difficult job. To start with may be difficult. But again, the advantage is that you can see the effect when you change something. And so that's the last point I said, that user defined arbitrary path. So I am telling that you calculate the path. If I cool from 800 degrees to 500 degrees in 10 years, or calculate the path if it cools in 10,000 years. So the difference I am telling it and it calculates. And finally, so these are the Himalayan map. I cut short it, and then we took these two different garnet crystals which show different diffusional zoning. You can see the thickness of the blue part is more on the left side than in the right side, so there must be some differences in the result of calculations as well. So the blue line are the X, that the compositions we are measuring, okay? And these are the results of the two things. Now in each curve, actually there are two curves. One is dotted, another is solid. The one is solid is the numerically model, that is our computer program is calculating, and the dashed one is the actual that the electron probe analyzer analyzed. So you can see how close they are, and this similarity was brought by iteration, hundreds of iteration. And I have the full program, but there's no time to show you the use of the program, that if I change then this matching goes away. So I have one for this sample CLN, I have this diagram, and for another sample TG8C I have this diagram. You see wonderful matching, and fortunate that the matching, there is a small kink there. This kink is because that particular point the electron probe beam fell on a hole, because it's an arbitrary hole there. It fell on the hole, so it did not analyze anything. And so that shows that it is a genuine natural case that is bound to happen in nature, because you polish, not everything is as smooth as possible. So these things will happen, and this is good. And then my program then calculates the cooling history, that is the composition versus time. The two samples are quite different. One is has cooled by 45 degrees Celsius per million year, another by 500 degrees Celsius per million year. So you could say 10 times, forget about the number, but it's 10 times faster. And 10 times faster means it must have come up faster. Then only it cools. At depth it is still hot, so it must have come up faster. And if it comes up faster, it must have caused lot of natural hazard at that time, because the area will be lot of earthquakes if the whole mountain comes up so fast. Thank God we were not there when the Himalaya actually came up. But it is coming up as of now. As you know, the Everest is increasing 1 inch per year. And the effect you can see in Uttarakhand, you can see in 2015, Nepal, everywhere. A slight change will cause the devastation of killing of lakhs of people. So these are direct usage in the natural case. And then so that is what we got, that within this entire yellow portion, that one portion came up at 500 degrees Celsius cooled, another one came up at 45 degrees Celsius. So there must be lot of things happening along the boundary between the two. So I am not going into the geological significance here, but the point is that I tried to explain that these are possible to calculate. So the first question is answered, how fast the rocks cooled. Now how fast the rocks came up. So I take one of the values here, and I use the one-dimensional heat conduction generation advection equation to solve for this. For these, each parameter we calculated from the natural rocks. For example, the heat production, we calculated with the help of analysis that how much potassium is there. So potassium is the main heat producing element in the rock. So how much it is decaying, how much heat is produced. So these are all numbers that we got by analysis. And of course, the density one can calculate easily. We calculated heat capacity, calculated, everything is calculated. Thermal diffusivity data was taken from sources, and from that we try to calculate the rate of uplift, that is the Vz, the velocity of uplift. And that's what we get when we try to fit. This is our paper. We showed that the Vz varied from 15 millimeter per year to 2 millimeter per year. So it started with coming up very fast, 15 millimeter per year. Now in geological significance is quite a lot. And then somewhat a stable condition came into, so then the uplift became slow, only 2 millimeter per year. So that's the best fit that we got from here. So this is the answer to the questions B, how fast the rocks came up from the depth. First 15 millimeter per year and then slowly 2 millimeter per year. So these were the questions and these were the answers that we arrive at almost 0.00 time. So these are the questions that we arrived, and this is how, and this is the references of our work that you can see, and this is our part of our Sikkim crowd that we went there and did this fieldwork jointly. It was a multinational group of 8 different countries. We worked very cohesively, very unlikely for Indians. I must say that we worked very cohesively for the 8 international collaborators, and things worked out very nice, and we could visit those beautiful places. So thanks to the organizers of this meeting for asking me to come, and these are my collaborators who helped me, and of course my students for the last 44 years, so they contributed maximum to my growth. I mean, without them I am nowhere. And these are the funding agencies, and Indian Statistical Institute is thanked for hosting me. Thank you very much.